Hey everyone, and welcome back, Focus Learners, to another explainer. Today we're exploring the absolute bedrock of modern engineering. We're going to unpack the hidden mathematical pillars that make, honestly, almost every piece of advanced technology around you possible. I'm talking about two really profound concepts from systems theory: controllability and observationality. If you've ever wanted to understand how humanity basically conquered the physical world through automation, you are in the exact right place.
Okay, let's dive into this. Have you ever wondered how engineers manage the seemingly impossible task of controlling incredibly complex systems? Like, think about a spacecraft hurtling through the vacuum of space. You've got thrusters firing, gyroscopes spinning around, fuel sloshing around, unpredictable external disturbances, and yet you can't possibly attach a physical sensor to every single moving molecule or gear. It's just not possible. So how exactly do you steer something that you can't entirely see? Well, the answer lies in the beautiful mathematics of control theory.
Here's our structural roadmap for today. We'll be looking at controlling the modern world, stepping into state space, Pillar 1, which is controllability, Pillar 2, which is observationability, the principle of duality, and finally, designing the perfect system.
Part 1. Controlling the modern world.
Pretty much our entire modern quality of life, from the second you wake up to the time you go to sleep, relies entirely on complex automated engineering. Without these invisible control systems, our world would literally grind to a chaotic halt. And the secret sauce making all of this reliable automation a reality is called feedback control. Think of it as a continuous loop. The system is constantly monitoring its own output, comparing it to what we actually want it to do, and then instantly correcting itself to compensate for any external disturbances or random errors. It is the ultimate self-correcting mechanism.
Just to ground this in reality, feedback control is the invisible hand you interact with every single day. It's what makes a high-speed elevator perfectly level with your floor without jarring your knees. It's the core logic allowing autonomous vehicles to steer themselves safely down a highway. It's even what keeps a communication antenna perfectly pointed at a satellite even while it's getting absolutely battered by heavy winds.
Moving on to Part 2, stepping into state space.
To wrangle these modern, incredibly complex machines, engineers quickly realized they couldn't just rely on basic equations anymore. They had to invent a completely new mathematical arena. By definition, state space is the n-dimensional mathematical space whose coordinate axes consist of all the state variables needed to completely describe a dynamic system's behavior. Now, what does that actually mean in plain English? It means instead of just looking at, say, one input and one output, engineers created a math model that lets them look at the complete internal status of a system at any given microsecond. Every velocity, every temperature, every single position gets its very own coordinate.
So the really crucial point here is the shift from classical to modern control. See, classical control theory was great for simple things: one input, one output. Think of like a standard household thermostat. But modern control theory, which is driven by state space, can handle multivariable, highly complex systems. Imagine a modern aircraft with hundreds of inputs and outputs all functioning simultaneously. State space basically tames that complexity by bringing all those scattered variables into one unified mathematical framework.
Which brings us to Part 3. Pillar 1, controllability.
Before an engineer actually builds a complex dynamic system, it has to pass the ultimate mathematical test. We have to know definitively, can this thing actually be steered? Here's how the textbooks formally define it. Controllability is when an unconstrained control can transfer any initial state to any other desired location in a finite time. Put simply, it means there are zero dead zones. It means your steering wheel and your pedals are actually capable of driving every single part of the vehicle exactly where you want it to go, without anything getting stuck or left behind.
But, how do you prove that without physically building the thing first? Well, you don't need endless calculus. Engineers just look at a specific matrix from their state space model called the Controllability Matrix, or P sub C. They run a really quick calculation to see if it has what mathematicians call full rank. If the determinant of this matrix is non-zero, boom, it has full rank. And that is the mathematical green light, meaning you have absolute total control over every variable in that system.
And this brilliantly illustrates the difference. A controllable system is perfectly driven. Every single variable is reacting exactly to your input commands. An uncontrollable system, on the other hand, has a disconnected subsystem. It just does its own thing, completely ignoring what you tell it to do. Imagine if your car's brakes were physically disconnected from the brake pedal. That is an uncontrollable state. And checking that matrix ensures engineers never actually design a system like that in the real world.
All right, Part 4, Pillar 2, Observability.
So we just mastered our ability to act on a system and steer it. Awesome. But now we have to shift gears and focus on our ability to measure it. We have to be able to see what we're doing. Here is a massive real-world engineering problem for you. What if you can't measure everything? What if sensors are just way too expensive to put on every single gear? Or what if they're too heavy for a really lightweight drone? Or what if the hardware is buried deep inside a nuclear reactor, where a sensor would literally melt? We can't always physically measure every single part of a machine.
The solution to this problem is just pure genius. Engineers use what's called a state observer. This is a mathematical subsystem. Think of it basically as a really clever software algorithm that reconstructs or estimates the unmeasurable internal state variables. And it does this based solely on the inputs going in and the outputs coming out. It acts entirely as a virtual sensor. Just by looking at the outside of the machine over time, it magically deduces exactly what is happening hidden away on the inside.
But, just like with steering, we absolutely have to prove this is mathematically possible before we start relying on it. So engineers check the Observability Matrix, or PSOB. Just like before, they are looking for that full rank status. If it has full rank, it guarantees that no internal state can hide from your output data. Every single internal change will eventually leave a tiny fingerprint on the system's output, meaning your virtual sensor will always be able to figure out what's going on.
Part 5. The principle of duality.
This is the point where these two massive, seemingly independent concepts, controllability and observability, collide in the most beautiful way. And we have to introduce an absolute legend in the field here, Rudolf Kalman. He was the central figure in mathematical systems theory back in the 1960s. You've probably heard of his super famous Kalman filter, which, by the way, was literally instrumental in getting the Apollo spacecraft safely to the moon. Anyway, Kalman noticed an incredible, highly elegant realization about our two pillars. Now, what's really interesting about this concept is Kalman's principle of duality. Controllability is the ability to steer, right? While observability is the ability to see. One is based on inputs and actuators, the other is based on outputs and sensors. Well, Kalman proved mathematically that these two problems are exact duals of each other. They are perfect, mirrored mathematical reflections. If you know how to solve the math to steer a system, you automatically know how to solve the math to see inside it. It is honestly one of the most profound shortcuts in the history of engineering. And finally, Part 6, Designing the Perfect System.
So, how do control engineers actually use these twin pillars in practice today? How do we go from abstract theory to real-world technology? Well, it boils down to a strict three-step design process. Step 1, check the Controllability Matrix to guarantee we can steer the system. Step 2, check the Observability Matrix to guarantee our virtual sensors can actually see the system. And once both of those math checks pass with flying colors, we move to Step 3. We actually design the controller to command the system and the observer to track the system. We use advanced math to basically place the system poles, ensuring the whole setup responds super fast and remains perfectly stable.
And all of this relies on one final beautiful engineering trick, the separation principle. Thanks to the math Kalman and others developed, you can design your feedback controller and your virtual observer entirely independently from one another. Like, completely different teams can work on them. But when you finally connect them together in the actual machine, they are mathematically guaranteed to seamlessly work together without causing the whole system to crash. It's pretty much the ultimate divide-and-conquer strategy for complex engineering. Which leaves us with this final thought. The math we just explored literally powers today's world. But as the Internet of Things rapidly connects billions of autonomous devices, we're talking everything from self-driving cars to massive smart power grids, the sheer complexity is skyrocketing. So how will we guarantee controllability when the unseen variables become almost too complex to observe? It is a thrilling challenge for the next generation of engineers to figure out. I really hope this explainer gave you a deep appreciation for the hidden math steering our world. Stay curious, keep focused, and I'll see you in the next one.